we're back. And so what we have, here are the two balls we're going to charge, okay? This one here is mounted on this little stand that I can slide along the apparatus. And there's a, if I can get it to show up, there's a convenient centimeter scale showing how far, this is not actually, you see, 0 is over here. And the other ball is over here. This shows you the distance between the centers. If I slide it right over so that the one bumps into the other, well, that's the end of the track right there. There's still a couple of centimeters between the centers because of the size of the balls, okay? So it doesn't read 0 there, it reads a little bit less than 3. But this scale shows the distance between the centers of the balls, and I can slide that around. What I'm going to use to charge these up with is I've got this power supply over here, and I'm going to crank it up to 5,000 volts, and I just take the for the ground wire. Okay, this one here, you probably can't read it, but it says 0 volts next to that socket. And if you follow the black wire, I've just attached it to the base of the apparatus with this alligator clip here. So that means that all of this is at a potential of 0 volts. And then the red wire, exhibit B here, that's plugged in to the high voltage outlet there. And when I turn the thing on, that'll have 5,000 volts. Not much of an electrocution hazard, if anybody's wondering about that. It's like, geez, houses are only 120 volts and people get electrocuted all the time. Yeah, but this power supply has a lot of internal resistance, okay? So it's not capable of putting out even a substantial fraction of an amp. It's the amps that does the damage to you. And so the voltage is just how hard it's getting pushed. Well, I'll talk about that more in class another day. But when I want to charge these things, I will just touch them. This is my magic wand. And when I touch you, you turn into a pumpkin, or in this case, you become electrically charged. I am hoping that I can just, like I said, the weather's a little on the dry side. I'm hoping I can run through the whole experiment without having to recharge the balls. The way we measure the force is, let's see. Well, right now the balls are uncharged, and also this one is as far away as I can get it. And so this thing ought to read 0. Okay, there's a dial on top here that I've got set to 0 at the moment. And when there is no force and the dial on top is 0, these marks here on the torsion balance and here on the supporting structure, they should line up with each other. And the fact that they don't means it's a little out of adjustment. See this ball and the arm it sticks out of, and this thing back here, I don't know if you can even see it because it's fairly fine, but there's a vertical wire. The bottom of it is here, and this skinny little wire, maybe it'll show up better if I put a piece of white paper behind it. Kind of like, yeah, you can kind of see a gray line there, kind of skinny little line. Goes from here up to, goes through this little plastic doodad here, and then continues on up to this connector, which is on the bottom of the knob. Okay, when you turn the knob, what happens is it twists the wire. That's all there is to it. The knob twists the wire. So if I bring, these will have like charges. I'm going to charge them both in the same way. So they'll repel each other because they're like charges. If I bring this close, the electrostatic force pushes this away. And I will bring it back to its original position by turning the knob, which twists the wire. The harder that the electrical force pushes on the ball, the more I have to twist the wire to bring it back. And how far I've twisted the wire can be read off of the dial there. So that's how it works, okay? And of course, how it works is what I'm always looking for you to explain when you write up the discussion. Run through that one more time. The harder the electric force pushes this, the more I have to twist the wire to bring it back. And measuring how much I've twisted the wire will tell me the force. Not in newtons, but in some arbitrary unit that we'll just use for purposes of this experiment, okay? So before I can start though, the thing has to be correctly zeroed, which means there's a little bitty thing under here I can turn, and I need to get those marks to line up. And of course, you always turn it too far, or maybe not far enough. One problem with this experiment is always air currents. That torsion balance that we used for the gravitation lab last fall is all enclosed inside of a little glass box. This one, on the other hand, is out in the open, which you can kind of get away with because we're not trying to measure such ridiculously small forces. But just the same, it has a tendency, if you watch it for a minute or two, you think you've got it zeroed just right, and then it moves a little, and you adjust it, and then it goes back like you had it right the first time. And yeah, so right now it looks like I've overshot a little bit. Let me try bringing it back some. And all I'm doing is turning the little plastic nut on the bottom that the wire goes through to twist the wire ever so slightly one way or the other. And I am going to call that good enough. Cross my fingers, hope for the best. Okay, so I think we're to the point where I should actually start reading the directions. Part 2, apparatus. Just describe the apparatus. Procedure. Connect the wires and don't touch the metal tip of the 5,000 volt probe. Step 2, check the zero. Just did that. Number 3, turn on the power supply. Set it for 5 kilovolts. Slide the ball to R equals 15. Yeah, any farther out than R equals 15, the forces seem to get too small to reliably measure. So R equals, this will be our outermost measurement. There, can you see that? Sort of, I guess. You know, I've got it on 15. And I turn on the power supply. Correction. I plug in the power supply and then I turn on the power supply. I have heard that referred to as the first law of electronics. It works better if you plug it in. Okay, turn it up a little more, somewhere around there. And touch that one. point you where you can see what I'm doing. Touch that one and touch that one. And then here and look at those marks and see it's being pushed away by the electrostatic repulsion because the two things are like charges. And I'm now turning the dial. And maybe I need to go just a little further. There, look good to you? Looks good to me. Well, actually, if you wait a moment, no, I need to go a little further. Yeah, at first it looks like I've gone, okay, now I think I've got it. And can you see the numbers? No, they're all blurry and nasty. Come on, focus. 14. I'm gonna write that down. If I can figure out where I put my pen, I will write it down. I really did have a pen here a while ago. 14. Next reading, 12 and a half. So we slide that up to there. And that looks like a white blur without any marks on it on the monitor. Okay, there it is, 12 and a half. And I see closer, it's pushing on the thing harder. So I have to twist the wire farther. So turn the knob some more. Bring it to where the marks line up. Give it a minute to settle down. I may have overshot, or it might just sort of swing back if I am patient. Yeah, I think I need to back off a little. A little more. Why don't we go with that? That being, can't make up my mind between 23 and 24. Well, let's call it 24. Next stop, 11 centimeters. Once again, it's been pushed away by the now stronger electrical force from the closer charge. So turn the knob a little further and give it a moment to settle down. I think I might have hit it on the first try. How often does that happen? Okay, and up here on the dial, focus. There it is. We got a nice even 30. Ten centimeters is next. Right there. Turn the knob. Maybe turn the knob just a little bit more. Can't decide if that's okay or if, of course, you look at it on the, I think I need to back it up just the tiniest bit. There, I like that. And up here we have 39. Nine is next. 9 centimeters. Right there. Again, that's the distance between the centers of those two balls. So we come down here. Once again, the force has increased, so we have to increase how much the wire is twisted. As I said, these forces are not in newtons. What that dial is actually measuring is how many degrees the wire has twisted. And I believe I've overshot. Yeah, let's use that. 49. Well, maybe you'll, oh, there it is. Just shy of 50, 49 for the force at 9 centimeters between the centers of the balls. Slide it up to 8. That's about the spot. Turn the dial. Those little rings, by the way, if anybody's wondering what they are, they just, you slide them on there for counterweights to make the thing balance, is all they're for. Kind of looks like I went just a degree or two too far. Yeah, maybe I should still back it off by another degree or so. Yeah, that's looking pretty good there, I think. We are at, come on, focus, 61. I don't think this is going to work too badly. I am encouraged. Now we go to 7. That looks pretty 7-ish. And once again, the ball on the right has been pushed away by its repulsion from the ball on the left. And so we twist the wire to bring it back. A little further, I guess. And maybe just a tiny bit more, like another degree or two. So you have to bring it back to the original position so that these numbers along here are accurate. This is the distance from the center of the one ball to the center of the other when those marks line up. Oh, now I see it drifted a little bit. I may have gone just a bit too far, except it's coming back now as I stand here talking about it. I'm going to back it off by just a degree. Maybe even another degree. It'll be that way. All right, I'll back it off another degree. Hopefully it's not because the thing is discharging. You know what? I think I'm turning it the wrong way. That's what I'm doing. So yeah, I'm pretty much back where I started. Anyhow, here's what I've got. It's kind of in the middle, 77 or 78. Maybe a little closer to 78. You can see it. Well, you could a moment ago. Use your judgment. I think 78. Okay, last one is 6 centimeters. Now, actually, we could slide it even a little further down the track than this, but the problem is, once the balls start, and we could even have a little bit of this here at 6 centimeters, when the balls start to get close to each other, like they're pretty close now, they start to polarize, okay? It starts to get so that you have a negative side on one side of the ball and a positive side on the other side of the ball. And this whole assumption that you have in Coulomb's law about it being point-like charges kind of breaks down. Things get more, or let's say equivalent to a point-like charge. Things get more complicated. You can get an attractive force superimposed on top of the Coulomb repulsion, and so 6 is about as close as we dare to go, even though I could go at least another centimeter along the track without the balls touching. It's not a good idea because, like I said, super close, things get more complicated and you get bad results up in there. So yeah, I think that lines up. And we've jumped up to a fairly high number for the last reading here. Come on, focus. The people want to see. Well, that's almost focused. There, if I hold it here, I guess it shows up pretty well. We've got about 98. And that concludes the data gathering portion. I'm going to pause it, and don't go away yet. Yeah, I just paused it for a minute to make sure it was going to work out all right, because, you know, I didn't quite follow the directions. It says to recharge the balls between trials, but as I said earlier, that becomes important in warm, humid weather, but it actually, there's what the graph looked like when I did it.